All right. Well, hey everybody. Obviously, you've heard that Ohio State has canceled face-to-face classes until March 30th at least. So I'm going to try to do my best to make sure that I record these videos in the nicest green screen studios that I can. Try to make sure that you guys get the same kind of physics experience that you would. It's almost as if I'm in the same room with you. It's almost as if it's the same. Um, but we'll do the best that we can. I'll try to make as many good jokes as I would normally do in the room, and you can cringe if you want. But in any case, let me know if yeah, send me. I'll be checking my emails regularly to make sure everybody's on the same page. So same song and dance. We're going to do a lecture. We're going to do a worksheet at the end. And just go ahead and submit that worksheet. You can print it out and fill it out, or you can do it on your iPad and use your Apple Pencil to fill it out that way. And so you can either take a picture of it with your cell phone, or you can just save the edited PDF and send that back to me. So the lectures at least should be pretty similar to before. So all right, so let's jump into it. We've been talking a lot about magnetic fields. We've been talking about how changing magnetic fields produces like a voltage, an electromotive force. There's an electric field associated with that. Today we're going to talk more about connecting these ideas with circuits, with something called inductors, which maybe you've heard of before. But that's what we're going to do. That's what we're going to do today. It's going to be a continuation of what we've been talking about. So a solenoid is an example of an inductor. We've been talking a lot about solenoids. And so those are two different names for the same thing, basically. And we're going to talk about what happens when you put a solenoid type thing into a circuit that has a resistor in it or a capacitor. And so that's where things are heading. I think what we're going to do is we're going to go ahead and review a little bit. So what's interesting is that I think this is a new. I think this is actually a new thing. All right. So we're going to talk about solenoids, and another word for a solenoid is an inductor, or a solenoid is a type of inductor. And so we're going to continue talking about that. And then we're going to talk about what happens when you put a solenoid into a circuit, either a circuit that has a resistor in it or a circuit that has a capacitor in it. So that's what we'll be talking about in just a second. Now the basic idea of this is that whenever you have, so let's say you have some sort of a magnetic field here, as we discussed, that if you have a changing magnetic field, that produces an electromotive force in the circuit, right? So we've talked about that, and we talked about how if it's increasing, then the current goes in a particular direction. If it's decreasing, it goes in the opposite of that. But what's interesting is that if you, and this is the new idea, is that let's say that there is no external magnetic field, and the Earth's magnetic field is very small. So let's just say there's no magnetic field externally to this loop. But as you're turning it on, the current in this loop will be changing. Okay, so as you're turning this thing on, the current as a function of time goes from 0 to something non-zero, right? And so the magnetic field created by these wires will be changing, right? So that's going to create a magnetic field. It's going to do something like this, right? So if the current is this way, then that's going to be into the page on the inside. If the current is the other way, then the current's the other way. But it's going to create some kind of magnetic field like this. And by the way, it's that's going to create some kind of magnetic field like this. And but this magnetic field is changing, and so if the magnetic field is changing, well, then the magnetic flux from all this is also changing. If the magnetic flux is changing, well, then it's going to be an induced electromotive force and a voltage on this loop of wire, which is kind of remarkable. So if the magnetic field is changing, the magnetic flux is not just going to be the same. If the magnetic flux is changing, well, then you get an electromotive force. Let me start that over again. All Okay, so we're going to be talking about solenoids like we've been. Another word for a solenoid is an inductor. And so we're going to talk about what happens when you put solenoids into circuits that have a resistor in it, what happens when you put it into a circuit that has a capacitor in it, things like that. And the basic idea that we're going to talk about today is that we're going to be building off this idea that we talked about how if you have a uniform magnetic field that is changing, either getting stronger or weaker, that produces a changing magnetic flux, which produces an electromotive force, in this case, which can cause current to circulate. But the new idea now is that anytime you turn on a circuit, the current in that circuit goes from being zero to something non-zero, right? So if you have some current there, and if you have some current there, that's going to produce a magnetic field. And if that current is changing, well, then that magnetic field is changing with time, which means that the magnetic flux in this situation is not going to be the same. And so if that magnetic flux is changing with time, that's going to produce an electromotive force, which will produce a voltage on our loop, and that's going to cause, that's going to affect the way that the current flows in our loop. And so this is kind of you could say this is a self-induced electromotive force. And this happens in every circuit that you can think of. This happens. We haven't talked about it until now, just because it tends to be a small effect. The exception being solenoids. So solenoids, this is a big effect because you have lots of wire wraps, and so if there is a changing flux, that does make a huge difference. But if you just have one loop of wire, then it's not such a big deal. But all currents create magnetic fields, and at some point that magnetic field is going to change, either when you're turning it on or when you're turning it off, or maybe there's some sort of a blip in the power grid or something like that. All these circuits at some point will have a changing magnetic field, so all circuits at some point will have a self-induced electromotive force to some degree. And so we need to sort of factor this into the way that we think about circuits, so we can understand this. Like I said, normally the self-induced EMF is small. Maybe the magnetic field strength is small, or the loop is small, or the number of wire wraps is small. So in a lot of cases, it's totally fine to just kind of ignore this. But for solenoids, this is not quite true. So let's think about this for solenoids a little bit. So here's our solenoid. We have current, going this way through the solenoid and coming out the other end. We have some length of the solenoid. I like giving a length sol for that length. And we can calculate what the magnetic field is for this. So if you go a few lectures back, you can figure out how to calculate the magnetic field for using Ampere's law, because there is a magnetic field, and the magnetic field would look something like this. So again, the magnetic field depends on the current. So if the current is changing, the magnetic field is changing. Because the number of loops isn't really going to change. The length of the solenoid is probably not going to change. But if the current is changing, that'll definitely produce a changing magnetic field. And so you can use this with Faraday's law to figure out what the electromotive force would be. So once you know what the magnetic field is, you can multiply that by the area to figure out the magnetic flux. And then you take the derivative of the magnetic flux, which isn't, this is another name this is often called Faraday's law, as we talked about. Take the derivative of this thing. Well, is the area of the solenoid changing? No, it's not. Okay, not changing. Magnetic field's changing, so I can take this derivative. Only need to worry about the magnetic field there. And then I can take the derivative of this. Well, the only thing that's changing here is the current, and so we end up with something like this. So all this stuff times the derivative of the current times the area there. Okay? So there you go. Okay, so we do that calculation get the magnetic flux, take the derivative of the magnetic flux, we get this is the self-induced electromotive force for a solenoid. Not a solenoid that is in an external magnetic field that's changing, but the EMF from the magnetic field that the solenoid itself is producing as that magnetic field changes. So this is the EMF, and what we typically do is we typically say, you know what, the only thing changing here is the current, and so the rest of this stuff is just a bunch of constants. So we'll say that the EMF is just a bunch of constants times the derivative of the current. So if the current is steady with time, then the derivative of it with time is 0, and the electromotive force is 0. It's only when the current is changing, which produces a changing magnetic field, which is what produces the electromotive force. So this makes some sense. And what we typically do is we typically say, all right, well, these constants, we're going to call this something. We're going to give it a name. We're going to call that the inductance. And typically we use the letter L to indicate the inductance. So if you kind of look at this expression here, you know, constant, 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 that means that for a solenoid, the inductance of a solenoid would be this, right? So it's the area of the solenoid, it's the number of loops divided by the length of the solenoid times the magnetic permeability. So if you put iron inside of it, you might want to change that to the value for iron. But that's what you get. Annoyingly, you know, the symbol is capital L, and so it's pretty easy to confuse with the length of the solenoid, the physical length of the solenoid. This has nothing to do with the physical length here. This is just, this constant relates to how much of a voltage you get when the current is changing. So it's a little bit annoying, but I'll try to make sure that I adequately label this when it's a length, and usually there won't be any label if it's just the inductance. So everything has an inductance. So solenoids are examples, but there's other sort of solenoid-like things. So I think a lecture or two back we talked about toroids that has like kind of a donut thing with wires wrapped around it. And so solenoids are not the only example. I think they're the simplest example, though, so we're going to talk about that. Now, in a circuit, you often see this symbol for an inductor. And this symbol is directly referencing sort of this kind of solenoid type thing. So here's what it might look like in an actual circuit there with iron inside of it to make sure the magnetic permeability is nice and large. But this is the symbol we're going to use in a circuit. Another example of a solenoid, like I said, is a toroid. So I don't think this is technically called a solenoid, but you can kind of see how it would do similar things to So what are the units of inductance? I'm glad you asked. So we know that this is the area of the solenoid, so that's meters squared. We know the physical length of the solenoid is meters. And then we also know what the units of the magnetic permeability is, so we can put that together and try to figure out what the units of inductance are. It turns out the magnetic permeability is something like this. There's a couple different ways of writing the units of magnetic permeability, but this is one of them. Well, that's amps down there, not to be confused with that. And then we have meters squared here and length there. So in terms of units, the magnetic permeability looks like this. That's what these little brackets mean. And so in terms of units, we have meters squared, meters, that, and so the meters, meter time meter on the bottom, meter squared, that's going to cancel out, and so you end up with the inductance being volts seconds over amps as our units, which we've not really seen before. And so whenever you have a new unit, you might want to give it a name. And so 1 volt second per amp is called a Henry. So often you'll see the inductance measured in H or millihenries or whatever. I believe Henry was an American scientist, USA. All right. Here we go. So we're going to put a solenoid into a resistor circuit with a battery. And there's an active figure in the book, which I think is pretty good. Let's see if I can bring that up here. All right, so here we go. So we've got a battery here. We've got a bunch of switches. And what I'm going to do is, in a second, I'm going to flip the switch so the battery is connected. and we're going to see what happens. And we're going to plot the current as a function of time. So I'm going to go ahead and leave this switch at A, so we're connected there. If it was at B, it wouldn't really do anything, right? Because if I click this, if I do this and then I connect the battery, it's not going to do anything, right? Because then this is making a circuit, and if that's making a circuit, it's not making a circuit with this. So if I click the battery on, nothing happens. So not too interesting, right? So let me click the battery off. What would be more interesting is if we keep that setting at A. So we keep that setting at A, we connect the, excuse me. We keep that setting at A. Now we connect the switch, and then the battery is going to try to try to force a current through the circuit. So when we do that, here's what happens. So we click that, and over time, the current gets larger and larger and larger. And so what's happening is that initially the current is changing. The voltage is changing, and so the battery is trying to push a current through this inductor. You can kind of see the current there with this purple line. But it can't do it because it creates a changing magnetic field in here, and if a changing magnetic field produces a voltage, and that voltage kind of counters the voltage from the battery, and so the current can't get through as much. But this is what happens over time. And then I can flip this switch and do that kind of thing. And so if you recall from our RC circuits, when we used to have a capacitor in this spot, we would charge up the capacitor, and then we would flip the switch, and then the capacitor would act as a kind of a battery that would drive current in this part of the circuit. This is a little bit similar, except that the energy is stored in the inductor instead of in the battery. So the inductor acts as the battery, and then once you flip the switch, the inductor drives the current in that part of the circuit until that energy is dissipated. Why is it dissipated? Well, we have a resistor here, and that resistor is going to get hot. And so you end up with this kind of decaying current over time. The inductor does not make for a very good battery, right? It kind of runs out of steam after a while, which is why we don't use them as batteries so much. But this is the kind of thing that one would get. So we're going to analyze this circuit in just a second and kind of understand why do these curves work out the way that they do. Okay, so let me switch back to this here, okay? So when we're discharging the circuit, so let's talk about when we just flip the switch. We've got current going through this, and we just flip the switch from A to B, and so now the inductor is gonna act as the battery. When you make this change, then it's as if this whole part of the circuit is just not even here. I'm gonna stand in front of it so you can't see it. Don't look. Okay? You don't even need to worry about that part either, right? So this is the only circuit that we need to worry about right now. And if that's the only circuit, again, thinking of this as kind of a battery, well then the potential drop across this thing should be equal to the potential drop across that thing, right? And so potential drop across the resistor equals potential drop across the inductor. Potential drop across the resistor, that's easy peasy, right? So that's the current times the resistance. And then the voltage across the inductor, well, that's going to be the derivative of the current times the inductance of that thing. Okay. Again, it's the self-induced electromotive force because of the possibility that the current is changing, which produces a changing magnetic field, which produces a changing magnetic flux. Anyway, so this is what you get. And now we basically have turned it into a math problem. So we want to know what the current is as a function of time. And all we know is that the derivative of the current is related to the current, and then the resistance and the inductance here are both constants, right? Because we're not changing the shape of the inductor, we're not changing the value of the resistance. And so we can try to solve for that. There's a couple different ways to try to solve for this thing. I would say the easiest way is to guess the solution, which sounds like a jerk thing to say. But it's always good to guess an exponential function in these things. So I'm going to go ahead and guess that the current is going to be decreasing like this. And what I really want to do is I really want to find this constant, this tau. It was called the time constant. I really want to figure out what that is in terms of R and L, or whatever else. But I really want to figure out what that constant is. This T is going to be the time. And then this I0 is going to be the initial current, right? Because if e to the 0, what's e to the 0, folks? 1, that's correct, okay? And so e to the 0 is 1, and so the current initially is just I0. So what I'm going to do is I'm going to stick this into this equation, and we're going to see what we get. So here we go. I'm going to stick that into there. And so to do that, I need to take the derivative of this thing, right? Because I have a derivative here. So the derivative of this, the derivative of an exponent is, say it with me, an exponent, right? It's an exponent, but you also have to take into account the 1 over tau thing here, right? Because of the product rule. Chain rule, product rule, one of the two. Anyway, you get a 1 over tau here, right? So I0, 1 over tau, there's a minus sign inside of this thing, so that comes out. And then you're left with, again, the derivative of an exponential is an exponential, so you get this. And so now you can stick this back up here and see what you get. Okay? So I'm going to go ahead and do that. So on the left-hand side, this is going to be I as a function time. We already know what that is, at least in terms of our guess. And so that's going to be this times R is on the left, right? And then this is from the derivative we just figured out. And what's interesting is that there's a bunch of constants here. The initial current cancels out. But more importantly, the exponential cancels out, which is really important because it has the time dependence there. And so you got a bunch of cancellations there. Initial current cancels out. Exponential cancels out. And the thing that you're left with is you got the R and the L and the tau, and you can solve for this tau, right? So you multiply both sides by R, divide both sides by R, multiply both sides by tau in order to get this. Okay, so we found that the time constant is the inductance divided by the resistance. And so if I increase the resistance here, how should that affect the discharge time? So I can go back to my little demo if it lets me. There we go. So instead of having a resistance of 1 kiloohm, I'm going to increase that to 2 kiloohms. Without increasing the resistance, it looks like this, just for context. So it's taking a little while to get up to the current, and then I can flip this switch. It takes a little while to sort of come back down. Okay? But if I reset this thing and I increase the resistance, again, we expect this to go a little bit faster. So if I connect that there, now we're not going to as high of a current because the resistance is larger, but overall it's going a bit faster to get up there. And then I can click this thing if I have time, and hopefully, let me just do that over again. But hopefully you see that it is going a little bit faster. Let me switch that back to here. All right, here we go. So climbing in current, that overall goes pretty fast, and I can discharge it, and hopefully you see that it goes somewhat faster than it was when we just had the resistance as 1 kiloohm. It's a little hard to see because of how the plot is changing and stuff like that, but indeed it is true. I can make it even more extreme by, so I already have the inductance maxed out at what they let me max it out at. And so remember, the time constant is L over R, right? And so if I make R bigger, that makes the time constant shorter. And if I make L smaller, that also makes the time constant shorter. Okay, so I'm going to decrease the inductance, and that should make it go even faster. So I'm going to go ahead and click this thing like that. And now I'm going to go ahead and connect it. And so that does look like it's going even faster than before. And now I'm going to try to click this thing. And yep, that does seem to go even faster than before. It's kind of a subtle effect because we're only dealing with factors of 2, so not huge factors, and also the graph there. It's a little hard to see, but indeed it is doing more or less what this equation is showing. So that works out fine. What's the other thing to say about that? Now, why is it happening like this? Well, it's interesting because you'd think that I just want to mainly talk about the fact that it goes as 1 over r here, because you remember when we had capacitors, the time constant goes as r times the capacitance. So more resistance requires more, involves more weighting for the energy to dissipate. This, it's the opposite. It's the more resistance you have, the shorter the period of time it dissipates. So what's interesting is that the reason this works the way that it does is basically that, let's switch that. The reason this works the way that it does is that the more resistance that you have, then the more quickly that you dump the energy. In other words, the more resistance, then the more quickly that resistor gets hot, and the energy that's in the inductor will be dissipated. So that's ultimately why that happens. In the limit that there is no resistance, well, then there wouldn't be any energy dissipation, right? And so it would take an exceptionally long time, basically forever, for this thing to dissipate. Which is actually one of the things we're going to talk about in just a second. So what if there is no resistor in this circuit? So in any case, the more resistance, the more quickly the energy gets dissipated. All right, I'm going to go ahead and close this out finally. All right, there we go. The next circuit I want to talk about, if I can get to the right screen, is an LC circuit. So like I said, so no resistor here, and there's no battery even. Instead, the capacitor kind of acts as a battery. We charge up the capacitor, and then we flip the switch, and we kind of see what happens. Okay, so what we're going to do is, what I want to do is that before we, let's just analyze this with some math before we do any kind of a simulation of it. So let's go ahead and do that. So to analyze this mathematically, thinking of this as the battery and this as the other thing, it would make a lot of sense if the potential drop across this thing is the same as the potential drop across that thing. Okay. So mathematically, the potential drop across the capacitor, do you remember what it is? So remember, Q equals C delta V, and so that means that V, or delta V, I guess, delta V is equal to Q over C, right? So Q over C there, and then the inductor is related to the derivative of the current, right? So Q over C, and then the inductance times the derivative of the current. Q can be changing with time, so we give that time indices. We should probably put time indices on the current here too, because that can be changing with time. But the capacitance isn't going to change because we're not changing the size of the capacitor, we're not sticking plastic in it or anything like that. And then the inductance, we're not changing like the shape or the length of the solenoid or not putting iron inside of it. So this inductance is going to be a constant. So constant, constant, not constant, not constant. And what we want to do is we want to be able to solve for what's happening in this circuit. So once again, it's good to be able to be a good guesser in these things. And it's never a bad idea to guess an exponential, right? Now, if we can't get this exponential to cancel out of the circuit, then we made a bad guess, and this hasn't necessarily given us any more insights. But a lot of times this works, not always, but sometimes it does. And so let's go ahead and give this a try. So we're going to go ahead and stick this in here. We're going to stick this, so this is the charge on the capacitor as a function of time. I can stick that up here, but I can also take the derivative of this to get the current, and I can take the derivative again to get the derivative of the current. Okay? And so that's what we're going to do. So the derivative of this thing, which will give us the current, is this. So we take the derivative of an exponential, gives you an exponential. So we had this from before, if you recall, is minus an exponential over tau. The next thing to do would be to take the derivative of this thing. And again, the derivative of an exponential gives you an exponential, but it also gives you this another factor, 1 over tau. Actually, it's another factor, minus 1 over tau, right? And so this gives you this, and then there's a minus times a minus, which gives you a plus. And so you end up with q0 over tau squared, like that. Q0 over tau squared, but the q0 times this exponential, that just equals the charge as a function of time. All right, so it's kind of clever going from here to here. Then we can show that this thing, right, so here's their di dt, this thing equals minus LQ over tau squared, right? Like that, okay? And what's remarkable about this is that the time dependence cancels out. So if I had, put this thing up here, the exponential would have canceled out, the time dependence. But another way to do it is just cancel out you have the charge as a function of time here, the charge as a function of time here. They cancel out, okay? So we did it. We got the time dependence out of the equation, which is what we were hoping to do. And now we can solve for tau, right? So multiply both sides by tau squared. Multiply both sides by c. That gives us this. And then we can take the square root of that. We get this. But now we have a problem, because the capacitance is always positive. There's no way to have a negative capacitance, okay? And then the inductance is also always positive. There's no way to have a negative inductance. And so the square root of minus LC is going to be the square root of a minus thing, square root of something that's negative. So this is a little weird. We haven't run into this yet. So I can take this. Well, let's just run with it. Okay, let's just leave caution to the wind and see what happens with this, and just see what happens. Okay, so this would be imaginary. So tau would be some imaginary thing times square root of LC. Let's just see what this does when you stick this into the exponential, which we can do. So I stick this into the exponential. It would look like this, right? Tau is equal to the imaginary times square root of LC. And you can do some sort of clever manipulations of that, right? So 1 over I, which is kind of what we're dealing with up here. So 1 over I, 1 over imaginary. We can multiply that by imaginary over imaginary, because that also equals 1, right? And so on the bottom, I times I is minus 1. And on the top, we still have I. So this thing we can rewrite as e to the it over square root of LC, basically. That's what we get. You can also write this as e to the I omega 0t, where omega 0 is 1 over the square root of LC. Okay? So if you plot this out, what does this mean? What does it mean to have e to the I omega t? Well, there's an equation that you may or may not have seen. Maybe you haven't. I don't know. But any kind of e to the I angle thing equals cosine of this angle, which in our case is omega t, plus the imaginary of sine of that angle. And so it basically gives us an oscillating function, right? Cosine is an oscillating function. Sine is an oscillating function. We're mainly concerned with the cosine, because that's going to be the real component. But this means that the charge on the capacitor oscillates like this. So for example, if I click this link on the previous page and kind of see how this works, hopefully this will come up. There we go. So we have a capacitor here, which is initially charged up, which is why you can see the positives and negatives there. They're illustrating the electric field, so there really is an electric field in there. And then we're going to flip the switch. And when we flip the switch, that allows the negative charges here to try to make their way back to neutralize the top plate of the capacitor. And when we do that, it will, so let's just see what happens. So I'm going to click that. And you see how the charge in the capacitor drops. Initially, the current's 0, but it kind of goes back and forth. So what's happening here? So let me start this over again. So again, the minus sign, the negative charges here want to neutralize the charges here. Initially, there's some trouble in doing that because that creates a changing current here, which kind of creates a voltage that sort of tries to prevent the current. So initially, there is no current in the circuit, but eventually, the negative charges here do ultimately neutralize the positive charges here. But what's interesting is that in that process, it produces a current in the inductor, and that current is changing, and so the magnetic field is changing, and if the magnetic field is changing, that produces a voltage. And so what happens is that instead of the capacitor acting as the battery, by the time that the electrons make it to neutralize the top of this thing, now there's a nice current going through here, and now the inductor acts as the battery. And the inductor actually is such a good battery that it will shove even more electrons on top of this thing to make it even more, instead of being neutral, it goes all the way to negative. And so you can kind of see the magnetic field develop in the inductor, and then vice versa. And so it kind of oscillates between one and the other. Now there's no resistor in the circuit, and so the energy never dissipates away. There's no way for a capacitor to dissipate the current, so nothing is really getting hot. Same thing with the inductor. There's no way for this inductor to dissipate anything as heat. Now in reality, the wire is always going to have some small amount of resistance to it, but to the extent that that resistance is negligible, it's just going to do something like this. And again, the reason has to do with this oscillating solution to the equation that governs this situation. One other thing to point out, if you're looking carefully at this, is that the magnetic field in the inductor, it shows you the magnetic field lines. Sorry, shows you the magnetic field lines, and those are the largest where the current is the most, and where the current is zero, that's when the magnetic field lines disappear there. So it's doing a nice job of illustrating that, and it's also doing a nice job of illustrating what's going on with the capacitor there. Now what's interesting is that there's actually a whole other part of this animation that I've kind of been hiding from you for your own good. So I can try to show you that part of it if I can grab on the right part of the window, like that. But this turns out, mathematically, this turns out to be basically the same thing as a spring mass system, which sounds ludicrous, but what's happening here is that you have the energy going from being stored in the spring to being in the form of the kinetic energy of the block, and then it sort of stretches out here, and the energy is stored in the extension of the spring until the thing comes to a stop, and then vice versa. If there's no damping in the system, it just sort of goes back and forth like that. And it's mathematically, this is the same kind of equation that we just solved for the circuits, except that it has nothing to do with circuits. It's just mathematically it's the same. And what's interesting is that in the olden days, back before I was doing nerdy computer stuff, people would actually use circuits to try to simulate what would happen in mechanical systems using these kinds of analogies. I think I might have a slide on that a little bit later. Okay. Now, why am I showing you a little fish that's oscillating back and forth? I promise you that this is still on topic for what we're trying to do. So I got this little toy from a conference I went to about a year ago. And I love it because inside of this thing there is a capacitor. You can't see it. There's a capacitor, and there's a little coil of wire that's wrapped around. It's a little bit like a solenoid. And then on this little fish thing, there's a magnet on the bottom of it. And what happens is that there's a little tiny solar cell here, which acts as just enough of a battery to kind of get things started, get the oscillation started, having the capacitor charged up versus having the inductor, having current through the inductor. And so this little solar cell sort of kind of starts those oscillations. And then once the current is oscillating back and forth, what happens is that this little fish thing, because there's a magnet on it, well, that magnet experiences a different force depending on whether there's a magnetic field on this coil. And so what ends up happening is that very naturally, if there's sunlight, that causes this fish to vibrate back and forth. So it's sort of hanging by a thread. I don't know if you can see the thread hanging from the middle of the thing. But the sunlight puts a little bit of energy into the circuit, and then that energy oscillates back and forth, and in the process it causes this fish to kind of wiggle back and forth. So this is kind of an ingenious toy because it doesn't need any batteries. It's only getting it only needs a slight amount of energy from the sun, and what they've done is that they've tuned the capacitance and the inductance of this thing to make sure that it's about at the right frequency to get this little fish to vibrate back and forth. So I think this is a really genius kind of gift, and it really is just a simple formula. It really is just a simple circuit that we just were thinking about. Now, one thing that's philosophically remarkable in all this is that I've been saying that, okay, so there's energy stored in the capacitor, right? You charge up a capacitor. You guys remember when I charged up the capacitor and then I disconnected it from the circuit and I held it and then I, made it do sparks, demonstrating that there clearly was energy held in the capacitor. So this is the formula for the energy held in the capacitor, which is that. I think it's also Q over C. So there's energy stored in the capacitor, but there's moments where the capacitor in that situation, the LC circuit, has zero charge on it, 0 voltage, but yet the circuit keeps on oscillating. And so what's happening in those moments is that the energy had to go somewhere. We haven't lost any energy because we don't have any resistors attached to the circuit. So where did that energy go? And I've already said it once or twice that the energy needs to go into the solenoid, into the inductor. And that's kind of remarkable because how do you store energy in a solenoid? There's no energy necessarily stored in the current. Like the fact that you have a current is not necessarily a source of energy. But in a certain sense here, this source of energy, you're storing it in the electric fields is what nerdy physicists would say. That in a capacitor, you're storing energy in the electric fields. This turns out to be the equation for the energy stored in a solenoid. So in a sense, you're storing energy in the magnetic fields. And so this V is not a voltage, by the way. This is the volume of the solenoid. So the bigger the solenoid, the more energy you can store in it. But it's remarkable because you're going from storing energy in electric fields to storing energy in magnetic fields. And later on in this course, this will turn out to be crucial for just the idea of electromagnetic radiation, the idea of sort of having fluctuations in electric field and having energy associated with that, and then having those fluctuations, storing that in fluctuations in the magnetic field and vice versa. So an electromagnetic wave sort of propagates by saying oscillating electric field, oscillating magnetic field, electric, magnetic, electric, magnetic, electric, magnetic, and that's how it gets from point A to point B. And so the fact that you can store energy in a magnetic field is important for the fact that photons traveling electromagnetic waves can also carry energy, which is good because it allows us to see and do all sorts of other fun stuff. Okay, so let's review this thing. I think I just said this aside about electromagnetic waves. All right, so let's say that you have an LC circuit with a battery, and you flip the switch. What happens when you connect the switch? So this is just sort of a quick quiz. This is a nice sort of midterm 2 practice. What did I just do? Okay. All right. So let's say you have a battery that. Okay. So let's say you have a circuit that has a battery, an inductor, and a capacitor, and you're going to flip the switch, and see what happens. So this is a nice question for, say, midterm 2. So what happens when you connect the switch? Do you have a current or do you not have a current in this case? What do you think? So the answer is that no, you cannot have an initial current. So if this was a resistor, then there wouldn't be a problem when you flip the switch and you want to drive current through this thing. Not a problem. The capacitor has no issues with going from 0 current to some constant current, right? Because you can charge up the capacitor. Eventually, the capacitor becomes charged up and blocks all the current. But we're not asking about after a long time. We're asking about what happens right after you connect the switch. And so the capacitor doesn't mind having a current, but the inductor does. The inductor cannot just go from 0 current to some constant current, because if you imagine the plot of that, of current going and then all of a sudden jumping up to some value, the derivative, the di dt of that, would be infinite. And you can't have an infinite voltage on this thing. That just doesn't make any sense. And so there's always going to be some delay from connecting the battery and having any kind of current there. So initially the current through the inductor is 0. This is a nice problem because this makes you think that there is a current, but because it's in series with this, there cannot be. Let's say that there is a circuit that has a battery and a resistor and a capacitor. So no inductor. So this is actually kind of a review. So we connect this. What happens when you connect the switch? Do you get a current or do you not? I think I probably just gave it away. When you connect the switch, you can have a current, again, because the capacitor doesn't mind being charged up. The resistor, as soon as you put a potential difference across that resistor, you can start moving electrons across it. And so you can have a non-zero current after you charge it up. After a long time, though, what do you get? Current or no current? Well, after a long time, this thing charges up into the point where the potential drop across this thing is the same as the battery. And if that voltage is the same as the battery, then there can't be any potential drop across the resistor. So there's no current after a long time. Basically, the capacitor can't be charged anymore, and so the current drops to 0. All right? Now, let's say that you have an RL circuit. So there's a battery there, you've got a resistor, you've got an inductor. Again, this is kind of a review. We talked about this earlier. What happens when you initially connect this thing? Can you get a current or no current? So after you connect the battery, remember that in an inductor, you cannot have the current going from 0 to some constant value as soon as you connect that switch. It takes time, right? Because jumping from 0 to a constant would be sort of an infinite di dt, and you cannot have an infinite voltage on this thing. That doesn't make any sense. And so initially the current will be 0, but after a long time, what happens after a long time? Well, after a long time, yeah, you can have a steady current through this thing. It's not a problem. Eventually that current steadies out, reaches a steady state, and so there's actually no potential difference across this thing because di dt is 0. And so you'd have non-zero current. So this is just a good review. So it's good to review those things. So there's a worksheet to work on that's associated with this. Let me take a look real quick to see what it is. The worksheet is, yep, so it's a circuit that has, you can see, worksheet looks like this. So we have an inductor, and then we have resistors and things. And the goal of this is to figure out how much current is flowing initially, right when you connect the battery, and how much is flowing after a long time. And so I've given you some examples of what happens to the inductor. And so this is a nice practical example. And again, I could easily put questions like this on midterm 2. So I hope you find this helpful. And send me an email if you run into any trouble. So, all right. Thanks, everybody.